Okay, so today I'll just be solving some problems on the heat and power integration, how to look at a bunch of process streams, how to extract um, your pinch point, your minimum energy requirements, and then from these, how to develop your heat exchange network, okay? And this is very important, just make sure you know how to do it because we have an exam. The exam is scheduled for next week, but I might push it to the week after um, because I want to make sure everyone is able to navigate through this process and be able to and be able to basically design these problems. Okay, so I'm gonna start. I posted this problem set on Blackboard, and we have two problems. There's actually three problems in the set. So I'm gonna go through them, and then towards the end, I'll go through problem 4 in the homework, which is sort of a unique situation. I don't want to start with this unique situation. Let's do some straight ones, and then we'll do sort of a curveball problem. Okay. So in these types of problems, you're usually given a table. This table has a bunch of information, stream information. You have your hot streams, you have your cold streams. And also, if you have any questions at any time, just unmute yourself and shout. Okay, so you have two hot streams and cold streams. You're given a heat capacity, or the heat capacity flow rate, which is usually in kilowatt per temperature. And then you're given a source temperature and a target temperature. This is the information you're given. The second piece of information you really need to look out for is your minimum delta T minimum, right? Or the minimum driving force temperature for these types of problems. Okay, so we're gonna go through the step-by-step process, and we'll solve these problems. So I'm gonna share the whiteboard. Okay, here we go. And let's start off just by writing the streams. Okay, just write what's given. So this is and in this case, I'm given a bunch of streams. And yeah, sorry for the wonky handwriting, but So I'm given a stream, I'm given a source temperature, I'm given a target temperature as well, and I'm also given the heat capacity flow rate, which is C, kilowatt per degree Celsius, okay? So in this case, I am given hot 1, hot 2, cold 1, cold 2, and the conditions are 180 to 80 and 135. So it goes from 180 to 80. Second stream goes from 135 to 45. Your first cold stream goes from 60 to 100 and then 35 to 120. 60 to 100 and 35 to 120. And I'm given the heat capacity flow rates for this problem, which are 13.5, 27, 53.5, and 23. So it's 27, 53.5, and the last one is what? 23.5. So let's do this step by step. Let me find my calculator here. Good, here we go. Okay, so step 1 is always subtract, and we're also given delta T minimum, right? We're told delta T minimum is 15 degrees Celsius, okay? So step 1 will always be to subtract delta T minimum from the hot streams. And only from the hot streams. And by that, I mean, I'm subtracting this delta T minimum from these four temperatures, both the source and the target. So 180 minus 15 will be what? 165. 135 minus 15, this is 120. 80 minus 15, this is 65. And 45 minus 15 is what? 30? Yeah. Right?
Yes.
Good. Okay, so once we do this, the second step would be to plot your, or define your intervals and identify your intervals and basically draw your streams or list your streams from highest to lowest. So step 2. And really, you should just follow the steps. And most of the errors come from not being organized or, losing your train of thought or doing some basic arithmetic errors, right? So arrange temperatures from highest to lowest. And identify your intervals. So in this step, I mean, usually if you look at your book or, any type of book, they do it differently. I follow the procedure from what's this guy's name? Timmerhouse, okay? And you just arrange them from highest to lowest. So what's the highest temperature here? It's 165.
Yes.
You had a question?
Oh, no, I was agreeing. I was saying yes.
Okay, good. So 165, and then next highest temperature was 120. Then we have 100, 65, 60, 35, 30. And this is also a step where a lot of calculation errors are made. Just finding or arranging temperatures from highest to lowest, it's very easy to just miss a temperature, right? And so you just try to be careful. And once we get to this point, actually, let me, once we get to this point, let me erase some of this stuff, just give myself some space.
So, Dr. Basha, I have a question.
Yes.
Since we have two 120s, are we going to put both of those in there?
It's just one temperature, right? It's
okay.
You just list the numbers from highest to lowest. This is really all you're doing. So we said 165,
Okay.
120, 100, 65, 60, 35. And after doing it, the easiest way to do it is to just graphically plot your intervals. So just whichever way works for you, but this is really the way which minimizes errors, and this is the conventional way to do it. When this method was developed, is you just plot or you just draw lines next to each interval. And then I'm gonna plot the intervals, I'm gonna plot my streams throughout the interval. So I have, my streams are H1, H2, C1, and C2. And in this case, I'll just draw them. So H1 goes from 165 all the way to 65, right? So I just start at 165. I draw a line all the way down to 65. H2 goes from 120 to 30. So I just start at 120 and just draw a straight line to 30, C1 goes from 60 to 100. So you start at 60 and you move to 100. And C2 goes from 35 to 120, right? 35, 120, and just, straight lines. And this way I can identify which interval covers, which stream covers which interval, right? because when I arranged my temperatures from highest to lowest, I can see that I have, this is my first interval, this is my second interval, third, fourth, fifth, and sixth. So I have 6 intervals in this system, and I know which stream covers which interval, right? So once you get to this point, I need to calculate some parameters, right? So for each interval, I need to build the interval table, and what the interval table really represents is just translating this figure into numbers, right? And your interval table will usually have 4 main columns. The first one is interval number. The second one will be your initial temperature for the interval. The third one will be delta T for the interval. And the fourth one will be summation of Cp hot minus summation of Cp cold. Okay, so let's calculate, or let's populate this table slowly. So I'm looking at interval number 1. So in this case, interval number 1. The initial temperature for this interval is 165. The delta T for this interval, or the length of this interval, is what? 165 minus 120. So what, 45. So I have 45 for delta T. And then summation of Cp hot minus summation of Cp cold. So how many hot streams do I have? I only have H1, and the Cp for this stream is 13.5. Minus any cold streams. There are no cold streams in this interval. C1 and C2 are not present here. So this parameter is only 13.5. Good. So then I move on to a second interval, interval number 2. My initial temperature in this case is 120. My delta T, so 120 to 100 is 20. And now I need to calculate my summation of Cp hot minus summation of Cp cold. So let's start with the hot streams. So summation of Cp hot is 13.5 plus 27. So this will be 13.5 plus 27 minus summation of cold streams, which is 1, which is C2, which is 23.5, right? Minus 23.5. And this value will be 13.5 plus 27 minus 23.5 is going to be 17. Okay, now let's look at the third interval. And really, it's a repetitive process, boring, all this stuff, but this is what you have to do, right, to design the system. So interval number 3, my initial temperature is 100. My delta T is 100 to 65. 100 minus 65 is 35. And then summation of Cp hot minus summation of Cp cold for this stream. So let's look at the hot streams first. I have H1 plus H2. 13.5 plus 27 minus my summation of cold streams, which is 53.5 plus 23.5. And if I do this addition rate, plus 27 minus 53.5 minus 23.5, I'm gonna get minus 36.5. Then we're at interval 4. Let's look at interval 4. So this is interval 4. The initial temperature is 65. The delta T in this interval is 5. And summation of Cp hot minus Cp cold. I have one hot stream here, which is H2. So it's 27 minus, I have 2 cold streams. So summing these two up, 53.5 plus 23.5. And this will give me 27 minus 53.5 minus 50, right? So I have minus 50 here. Interval number 5. So it's this guy right here. The initial temperature is 60. The height, or the delta T of this interval, 60 minus 35 is 25, right? And then summation of Cp hot minus summation of Cp cold. H2 is, so I have one hot stream, which is H2. It's 27 And I have one cold stream, which is C2, which is 53 point, no, it's actually 23.5, right? So C2 here is 23.5 and H2 is 27. Yeah. And this number will be 3.5. Okay. And now let's go on to the last stream, or last interval, sorry, interval number 6, which is right here. Initial temperature is 35, delta T is 5, and summation of Cp hot minus Cp cold. I only have one hot stream, H2, which has a heat capacity of 27. Okay, so now I populated my interval table. Now let's use this interval table to try and find the pinch point and the minimum cooling, minimum energy requirements, right? Minimum cooling, minimum heating, etc. needed for this system. So I'm gonna clean this up and I'm gonna move this table to the top left corner. And again, if you have any questions, please just shout them. So I'm gonna move this table here. So we said interval, Ti, delta T. And then I'm gonna add another column here, which is delta H. And delta H is basically summation of Cp hot minus Cp cold multiplied by delta T. So let's write them 165, 45. This value was 13.5, and this is in kilowatts, of course. 45 multiplied by 13.5, 607.5. Interval 2 is, we said 120, 20, and then this is 17. So this value is 340. Interval 3 is 100 to 35 minus 36.5. So I have 35 multiplied by minus 36.5. So I have minus 1277.5. Interval 4 goes from is 65. The length of this interval is 5. And this parameter here, difference in heat capacities, is 50. So this number right here is minus 250. Interval 5, we said it's 60, 25, 3.5. This is 87.5. Then finally, interval 6. Again, it's 35.5. This is 27. So I have 27 multiplied by 5 is 1. Okay, so I populated this interval table, and once you get to this point, you have all the information you need to build your cascade diagram, right? So I have my initial temperature of each interval, and I have my enthalpy in each interval, right? So let me remove these guys, and let's start building the cascade diagram. Okay, and to build a cascade diagram, the easiest thing to do is to start off by drawing a number of boxes equal to the number of intervals you have. So here I have 6 intervals. I'm gonna draw out 6 boxes. 2, this with 4, 5, 6. Okay, and then just connect them with arrows. It's just a graphical representation. We're gonna fill it out in a second with the numbers. And then once we have this, let's populate this using the numbers I have here. Okay, so on the left-hand side, you're gonna write your initial temperature of each interval. So at the very top, I have Ti is 165. And then in the box, you're going to write your enthalpy. And here, delta H in the first interval is 607.5. Second interval, the initial temperature of this interval is 120. The delta H in this interval is 340. I'm just reading the numbers from a table, moving them here. Third one, initial temperature is 100. Delta H here is minus 1277.5. We got to the fourth interval, initial temperature is 65. And the delta H here is minus 250. This interval, the initial temperature is 60. Oh, I forgot the H here. And the delta H here, 87.5. And then finally, the initial temperature is 35. And the delta H is 135. Okay, so I just populated it. On the left-hand side, I write the initial temperature of each interval. In the boxes, I write the enthalpies of each interval. Okay, so now I'm going to calculate one parameter, which is the heat in each interval. So in your base case design, you don't do if you don't add any heat, you don't remove any heat, just exchanging heat between the streams, your amount of heat put in is 0, so QH is equal to 0. After the first interval, 0 plus 607.5, 607.5, or we can call it Q1, maybe it's easier. This is Q1. Q2 here will be 607.5 plus 340. This is 947.5. Q3 here is 947.5 minus 1277.5. This is minus 330. Q4 minus 330 minus 250. This is minus 580. Q5 in this case, minus 580 plus 87.5. This will be minus 492.5. And then finally, minus 492.5 plus 135, and the very bottom is called QC, which is your cooling utility. So this will be minus 357. So any questions up to this point? So all we did really is define our intervals, calculate the enthalpy in each interval, and after calculating the enthalpy in each interval, we just calculated the heats in every interval. So if you have any questions up to this point or struggling to get to this point, please let me know now, and we can go over this again. Okay, so basically once you get to this point, we're looking at two things, or actually we're looking for one thing. And this thing is the Q with the most negative value, or the Q with the lowest value, right? Usually it will be negative. So in all the problems you're dealing with, it will be either negative or 0. And we're looking for this Q value, which is the most negative, okay? So let me have a look here. This is 0, okay. Minus 330 is negative, 580 is more negative, 492, no. So this is really the most negative value for Q, right? And once you identify the point which has the most negative Q, or the largest heat, the interval with the largest heat deficit, basically, you're gonna define two parameters. The first one is the pinch point, right? So I'm gonna define my first parameter here. So this will be my pinch point. The corresponding temperature will be my pinch point. And this is the point where I have no heat transfer across this point, right? So beyond this point, you don't have any heat transfers across these points between, the upper problem and the lower problem. So these streams or these intervals will exchange heat within each other. These intervals will exchange heat within each other, but I have no heat exchange between intervals here and intervals here. Okay, so once you define your pinch point, I'm going to define two parameters. my cold pinch, which is 60 degrees Celsius, and my hot pinch, which is equal to the cold pinch plus delta T minimum, right? So this is equal to TC pinch plus delta T minimum. So in this case, I'm not sure where this is. Okay, so in this case, this will be 60 plus 15. This is equal to 75 degrees Celsius. So I have my cold pinch and my hot pinch at this point. And once I get to the pinch point, I need to add enough heat so that the QH is equal to 0, right? So I need to add enough heat at the top of my cascade diagram so that the Q at this point is 0. So this is minus 580, so I need to add 580 at the top here. So I'm going to add 580 at the top plus 580. This will be 580 kilowatts at the top, and this guy plus 580. This will be 1187.5 plus 580 here. This will be 1527.5 plus 580 to this stream. This will be 250 plus 580 here. This will be 0 plus 580 here. This is 87.5. And then finally plus 580. This number will be, this will be 222.5. Okay. Hopefully we didn't do any arithmetic errors. But yeah, once I add enough heat so that my pinch point is 0, I have my minimum energy requirements, or the, the MER parameters for the system. And in this case, the QC is equal to 222.5, and the QH is equal to 580. 580. So from the steps, so this is the first step of your problem, I was able to define my parameters I need to build my heat exchange network. And in this case, these parameters were, my pinch point was 60 degrees Celsius, my QH was 580 kilowatt, and my QC will be 222.5 kilowatts, right? And these are really your energy parameters required to build your heat exchange network. Okay, so any questions about any of the steps to get to this point? How to build your cascade diagram, how to identify your pinch point, how to do any of these types of, or going through these steps. And really, you just follow the steps, take it slowly, just be organized, have your calculator, don't confuse a plus sign and a minus sign, and you should be fine. Okay, so if there are no questions about how to get to this point, we'll move on to the second part of these types of problems, where second part would be build a heat exchange network. You have your pinch point, you have your QH, you have your QC. Now it's time to build the heat exchange network. So let me write these on a piece of paper here so that I remember these numbers. So I have my T pinch, 60. QH is equal to 580 kilowatts, and QC is equal to, good. Okay, so I'm gonna clear this, what do you call this? Clear this blackboard. And so now let's build our heat exchange network. So again, to build the heat exchange network, you have the same type of algorithmic approach. So at this point, I have my T pinch is 60 degrees Celsius. My QH, we said, was 580 kilowatts. And my QC was 222.5 kilowatts. And now let's build the heat exchange network for this problem. And when building the heat exchange network, first step, again, it's a graphical type of approach. First step would be to plot your streams, okay? So I'm gonna plot them. So we had 4 streams in this problem. So you go back to what's given. So I have 4 streams. The first stream is H1. So I have H1, it goes from 180 to 80. 180 all the way to 80. And you just note that I'm using the original temperatures. I'm not using the adjusted temperatures which we use to do our cascade diagram. Just use the original temperatures and just plot your streams. H2 was from 135 all the way to 45. C1 in this case was from 60 to 100, right? So C1 is from 60 to 100, and C2 is from 35 to 120. So C2 is from 35 all the way to 120. So these are my 4 streams. I just drew lines, 4 lines, and I do the temperatures or listed the temperatures at the end of it. And now I'm gonna draw 2 horizontal lines representing the pinch points, okay? So I have 2 horizontal lines in this case. And you know, when drawing it on a paper, you can try to be a bit more organized in this. But anyways, so this is my pinch point, and I need to now list the temperatures for the hot pinch and the cold pinch. And if you recall, this is the cold pinch, so this is actually the cold pinch, and the hot pinch is this temperature plus 15, right? So the hot pinch will be 60 plus 15, or 60 will be 60 plus delta T minimum. And in this case, delta T minimum is given in the problem, which is 15. 60 plus 15 is 75 degrees Celsius. So once I draw my 2 lines for the pinch point, and for the hot streams, I'm gonna write my pinch temperature for the hot pinch, 75, 75, 75. And for the cold streams, I'm gonna write the temperatures for the cold pinch. So in this case, it's 60, 60, 60, 60, okay? So now I have my, so now I have my system basically. And once you get to this point, let's just have a look at the system and clean up this figure a bit. So for H1, I go from 180, 180 to 75, and then 75 to 80. So your temperature is decreasing, and then the temperature increases again. So this doesn't make sense. So I'm gonna erase this part right here. So H1 in this case only exists above the pinch, right? So I only go from 180 all the way to 80. This H1, it only exists above the pinch. There are no temperatures for H1 below the pinch. Okay, for H2, let's have a look. 135 to 75, 75 to 45, that's fine. So there's a split in the middle. For C1, I go from 60 to 60, 60 to 100. So this doesn't make sense. So I'm gonna redraw this guy. So C1 only exists above the pinch as well, right? So C1 will only exist here because I only go from 60 to 100. This is C1. And then finally C2, I go from 35 to 60, 60 to 120. This is fine, I'm increasing. And then the pinch point splits the stream in half. Good. So once you get to this point, now you have divided your problem into 2 parts. First part is below the pinch. Second part is above the pinch, right? Below the pinch is on this side. So this side here is called below the pinch. And when matching the streams below the pinch, you need to always follow these rules, which is CP hot has to be greater than or equal to CP cooled. And there is no heating below the pinch, right? There's no, you can never heat below the pinch. Okay, and above the pinch is the second problem. So this on this side, left-hand side is above the pinch. And in this case, CP hot is less than or equal to CP cooled. And there is no cooling above the pinch, right? You always have to remember this. Should never cool above the pinch. Okay, so once we divide the problems to above the pinch, below the pinch, we listed the rules of this game. As you can see here, it depends on the CPHs. So maybe it's a good idea to list the heat capacities for these guys. So for H1, it's 13.5. So I'm gonna write the CP. This is 13.5 for H2. It's 27. For C1, it's 53.5. For C2, it's 23.5. Okay, so I listed my CPs. Another good thing to do, or a good practice to do, you don't have to do this, but it makes your problem easier, is to calculate the delta H available above and below the pinch for each stream. So for H1, it only exists above the pinch. I have 180 minus 80 multiplied by 135. So that's 100, sorry, 13.5. This is 1350. So H1 has 1350 above the pinch. And you can also calculate the amount. H1 does not exist above the pinch. Maybe it's not a zero, it's just doesn't exist.
Dr. Basha,
Yes.
I missed that step. Can you repeat that one more time? How you got to that?
The delta H1?
Yes.
Okay, so basically I'm matching these streams. So this stream, so I've divided this system into two problems. So problem above the pinch and the problem below the pinch. And I need to match the amount of energy in the hot streams here with the amount of energy in the cold streams here, right? Basically, I need to match the delta H available with the delta H available here. Similarly, I need to match the delta H available here with the delta H available here, okay? So since this is a functional, or you will have to calculate the delta H eventually. So I recommend that you calculate it before doing any matching, right? You can do it while you're matching, but just list the amount of energy available in every part of each stream above and below the pinch, okay? And in a second, once we start matching it, it will be a bit clear why we're doing this. So I said here for H1 above the pinch, we said 1350. And for H1 does not exist below the pinch, so it has no enthalpy. H2 above the pinch, it's 135 minus 75. That's the temperature interval for H2 above the pinch. And if I multiply it by CP, I'm going to get my delta H. So 135 minus 75 multiplied by 1620. And below the pinch, I have 75 minus 45 multiplied by the CP, which is 27. So I have 810. For C1, it doesn't exist below the pinch. Above the pinch, I have 100 minus 60 multiplied by 53.5. So this is 2140. And for C2, it's 120 minus 60 multiplied by 23.5. This is 1410, whereas below the pinch here, it's 60 minus 35 multiplied by the CP value, which is 23.5. So this will be 587.5. Okay, so once we get to this point, we have all the numbers we need. So now let's start matching these streams. So I'm gonna look above the pinch. So above the pinch here, the rule of this game is CP hot has to be less than CP cold. So I'm gonna look at my first hot stream. It has a CP of 13.5. And I'm gonna look at the first cold stream. It has a CP of 53.5. And does this rule stand for this match? So 13.5 is less than 53.5. So I can connect these two streams and I can exchange energy between them. So I'm gonna draw my first heat exchanger for the system. So I have a heat exchanger here connecting the first hot stream to the first cold stream. And how much energy is this heat exchanger transferring? So this hot stream has 1350 kilowatts to give, and this cold stream needs 2140. So I'm gonna transfer all the energy from this hot stream to the cold stream. So I'm gonna transfer all the 1350 from this hot stream. This means that this H1 is done. So I don't need to worry about it. All its energy requirements satisfied. And for this cold stream, I transferred 1350, but I still have some heat left here in this guy. Okay, we'll deal with it in the end. So now let's look at H2. H2, CP hot, the rule is CP hot has to be less than CP cold. So let's look at the first cool stream, 27, 53.5. Does this rule stand? Yes. 27 is less than 53.5. Since I already connected one here, maybe I'll have a look at the second one. 27 versus 23.5. No, I can't really transfer heat between H2 and C2, right? Because this rule does not stand. So the only possible match is this guy, right? 27 and 53.5. Okay, so I'm gonna connect a heat exchanger here from this guy to this guy. And how much energy am I transferring, really? Let's see. So this stream, I already gave it 1350. So how much heat does it need? 2140 minus 1350. So it still needs 790 kilowatts, right? This stream can only can provide 1620. So it has more energy than what's required. So I'm gonna provide it. So I'm gonna provide it with all this 790, right? 790, 790. So now C1 is done. We've met all the energy requirements for C1. H2 still has some heat left, right? 790 from 1620, that's how much? It says 830 in this case. So after doing our initial pass, we connected H1 to C1 and we connected H2 to C1. H1 is all the energy requirements above the pinch are done. C1, all the energy requirements above the pinch are also done. H2 still has 830 kilowatts of energy to give, and C2 still needs 1410 from somewhere, right? Okay, so now I can't leave these numbers like this. I need to do something about it. And always remember, above the pinch, there is no cooling, okay? Absolutely not. Under any circumstance do you cool above the pinch. So even though you might be tempted to add a cooler here, just remove this 830, that's thermodynamically not valid, right? So you never cool above the pinch, should always heat above the pinch. Okay, so I have these 830, how do I deal with this? How do I deal with this stream to get rid of this 830? So in these types of problems where you've already done all your matching using the basic rule, you will need to split the stream. So at this point, I'm gonna create a split, right? Let's draw this properly. So I'm just taking sort of a split stream and reblending it later on, so that's fine. So I'm splitting this stream, and the logic of splitting this stream is because since the CP for this hot stream is larger than the CP for this cool stream, by splitting the stream, I can split the CP between these two streams. So let's say I do a 50-50 split, right? So the X here is 0.5 and the X here is equal to 0.5. This means that the CP in this stream is actually 13.5 and the CP in this stream is 13.5, right? So I just split the stream. This way I lowered the heat capacity flow rate in each of the arms of the split. And by doing so, I'm allowing energy to be transferred to this other stream, okay? So once I do this, I can now transfer all the heat remaining in the split stream to my cool stream, right? So now I'm gonna connect a heat exchanger from this guy all the way to this guy. And in this heat exchanger, I'm gonna transfer all the rest of this 830 kilowatts, right? 830. Technically, I mean, if you do the math, you would need to connect two smaller heat exchangers from each of the arms. But for graphical purposes, we just draw one heat exchanger from here to here. And this guy, I transfer 830. So this means that H2 is satisfied. So I met all the energy requirements. And now let's look. So the only stream left is C2. And I can add heating above the pinch because, you know, I can't add cooling. That's the logic. That's why I did the split, but I can add heating. So for the remainder of this energy, I'm going to add a heater. QH, it's a heater or, you know, heater. It's not right QH. Let's just write let's keep QH, doesn't matter. So I'm going to add a heater on this cooling stream, and the amount of heat this heater is going to provide will be the overall heat it needs minus however much was provided. So it will be 1410 minus 830, and this is equal to 580 kilowatts. And this number here should always match the number you get from your cascade diagram. And if they match, it means that this connection or this configuration is valid. If they don't match, then you have a calculation error or a matching error or something. Okay, does this make sense above the pinch before we move on to below the pinch?
Yes, it makes sense.
Okay, good. So now let's move on below the pinch. And below the pinch, I have two streams. And the rule of this game is CP hot has to be greater than CP cooled. So in this case, my hot stream is H2, right? It's H2 here. It has a CP of 27. So let's write it here, maybe makes it easier. And here I have C2, it has a CP of 23.5. So does this rule apply? CP hot greater than CP cooled? Yes, 27 is greater than 23.5. So I can connect these two streams. So I'm gonna connect a heat exchanger from this guy to this guy. And how much heat am I transferring across this heat exchanger? So this hot stream has 810 to give. This cool stream needs 587.5. So I'm just gonna transfer enough energy to satisfy this cool stream. So this will have 587.5 in this exchanger. And this way this C2 is done. And now here I can never cool below the pinch, right? So under no circumstances should you have a QC, a cooler, sorry, I can never heat below the pinch. So under no circumstance should you have a heater below the pinch. You can only heat above the pinch. Below the pinch, you should always cool your hot streams. So in this case, I need to cool the stream. So I'm gonna add a cooler, and the amount of energy in this cooler will be however much energy is left, which is 810 minus 587.5, and this will be equal to 222.5. kilowatts, and this number should always match the number you get from your cascade diagram. If they don't match, most of the time you have a small arithmetic error somewhere. Go revise your calculations. Most of the time it's an addition error, and fix these numbers so that it makes sense, okay? And once you get to this point, you have your heat exchange network developed, and this will be your proposed heat exchange network that meets the minimum energy requirements for this system or for this combination of streams, all right? And this is how you approach these types of problems. On the exam, you're gonna get, your exam will basically be 2 of these types of problems, give you maybe 2.5 hours, you try to do it, and that's it. You just follow the steps. There is, there are no differential equations, there's nothing, just follow the procedure, be organized, use your design intuition to do it. Okay, any questions up to this point?
Yes, Dr. Bosch, I have a question.
Yes.
So I know you said across the pinch there's supposed to be no heating. So in between the 2 red lines where you have the black from heater 2, and then you have the cool from cold stream 2, are we supposed to just assume they cancel each other out?
No. These 2 lines are just a graphical artifact. The idea of drawing 2 lines is to divide the problem to above the pinch and below the pinch, right?
Mm-hmm.
You can erase this part here. This part doesn't represent anything.
Okay.
I just didn't want to erase it, because if I erase it on Zoom, it's going to remove the entire line. So I didn't want to do it. But yeah, it has no effect. Once you split your problem above the pinch and below the pinch, and all your math adds up, it means all your energy requirements are done.
Okay. Thank you. That's all I wanted to know.
Right. Okay, so this problem one, let's practice another problem. So I'll just be practicing solving these types of problems today. So prepare yourselves. So let me clear this, and let's start with problem number 2. Let me share my screen.
Professor Basha.
Yes.
So when I was doing the homework, the last problem on there, the temperatures were in Kelvin and not in Celsius. So with that, and then the delta T minimum was in Celsius, did I have to convert the delta T minimum to Kelvin and subtract it, or do I just assume it was like an error or something?
No, just a comment about Kelvin and Celsius. It's good that you brought this up. So you know the conversion from Celsius to Kelvin, T Celsius plus 273.15 is equal to T Kelvin, right? So delta T in Celsius will always be equal to delta T in Kelvin, right? So this is just the conversion between the deltas, right? Just take a note of that. The only case, which I'm not going to ask you about it, but just to keep in mind, the only case where the delta T's are not valid if you have delta T in Rankine and you want to convert, to delta T in Kelvin is not valid, or delta T in Fahrenheit and you want to convert it to delta T in Celsius is also not valid, okay? But Celsius and Kelvin, the delta T's are the same.
All right, thank you.
Okay, let me share my screen for the second problem. So for the second problem, again, you're given a bunch of streams, and you're being asked to determine the pinch, minimum utility requirements, and design your heat exchange network for the system. Okay. And so I have my streams, and the second thing, my delta T minimum is 15 Celsius for this problem. So again, we'll follow the same exact steps and just solve this problem. So I have problem number 2. So the streams I'm given, I have stream, I have T source in degrees Celsius, I have T target in degrees Celsius, I have my CP in kilowatts per degree Celsius. So this guy, I have stream number 1 goes from 200, or actually let's write them H1. It goes from 200 to 80, and the CP value is 10. H2 goes from 155 to 50, CP value is 20. H3 goes from 90 to 35, and sorry, the CP value was 40. And then I have two cold streams. First cold stream goes from 60 to 100, CP value is 30, and the second cold stream goes from 8 to 35, and this, no, actually goes from 35 to 90. 35 to 90, and CP value is 8, right? So I have 10, 20, 40, 38, 200, 155, 90, 60, 35, 80, 50, 35, 190. Good, and I'm also getting that delta T minimum is 15 degrees Celsius, okay? So step number one, again, I'm gonna subtract delta T minimum from my hot streams only, from the temperatures of the hot streams. So delta T minimum is 15, so in this case, I'm gonna get 185, 65, 140, 35, 30, then again 35 minus 15, that's 20, 90 minus 15 is 75. Okay, so I have all my temperatures. I removed the delta T minimum, so that's fine. Second step will be to arrange them from highest to lowest and define my intervals. So let's arrange them from highest to lowest. What's my highest temperature here? It is, let me just draw a line.
185.
Yes, 185. So it's 185. And then I have 140, right? And 100, 90, 75, 65, 60, 35, 20, right? 1, 2, 3, 4, 5, 6, 7, 8. Did I miss something? 185, 140, 140 to 100, 100 to 90, 90 to 75, 75 to 65, 60, 35 to 20. No, it looks fine. Okay, so I arranged them from highest to lowest, and then I'm gonna plot my streams. So again, graphical approach is the easiest approach. If you're comfortable figuring it out yourself, do whichever way works for you. Just this approach minimizes errors, okay? And here I can see that I have a bunch of intervals. So how many intervals do I have? This is my first interval, second interval, third, fourth, fifth, sixth, seventh, eighth. Okay. Then I'm gonna plot my streams. So I have H1 first of all. It goes from 185 to 65. So I have H1 going from 185 all the way down to 65. I have H2 going from 140 to 35. All the way to 35. I have H3. H3, this guy goes from 75 to 20. C1 goes from 60 to 100. So C1 goes from 60 all the way to 100. And then I have C2 going from 35 to 90. From 35 all the way to 90, I have C2. Okay, so these are my intervals. I drew all my streams on it. So now let's populate the interval table, right? So I'm gonna draw my interval table here. And the interval table, just remember it has four main things. I have my interval number, actually five main things. Interval number, I have my T initial, the initial temperature of each stream. I have the delta T of each stream. I have summation of Cp hot minus summation of Cp cold of each interval, sorry. And then I have my delta H of each interval. So let's populate this table slowly. So I have my first interval, interval 1. Initial temperature is 185. The delta T is 185 minus 140 is 45. Summation of Cp hot minus summation of Cp cold. I only have one hot stream, H1, heat capacity is 10. So the number is 10 here. Delta H in this guy is 10 multiplied by 45, 450. Okay. Interval 2. Initial temperature is 140. Delta T is 40. Summation of Cp hot minus summation of Cp cold. I have two hot streams, H1 and H2. So this is 10 plus 20. So this is 30. And the delta H is 30 multiplied by 40. It's 1200. Okay, interval 3. The initial temperature of this interval is 100. The length of this interval, delta T, is 10. Summation of Cp hot minus summation of Cp cold. I have two hot streams, H1 plus H2, so it's 10 plus 20 minus one cold stream, which is C1. So C1 is 30, right? Minus 30. So in this case, 30 minus 30 is 0. So delta H in the stream is actually 0. Interval 4. My initial temperature is 90. My delta T is 15. Summation of Cp hot minus Cp cold. I have H1 plus H2 for the hot streams, which is 10 plus 20 minus Cp cold, which is C1 plus C2. 30 plus 8 minus into the bracket 30 plus 8. And this number is how much? It's minus 8, right? So this guy is minus 8, and delta H in this case is what? Minus 8 multiplied by 15 minus 120. So let me clean this up because I think I'm running out of space. So this will be minus 8, and this guy right here is 120. Let's have a look at interval 5. The initial temperature of interval 5 is 75. Delta T is 10, right? 75 and 10. Summation of Cp hot, I have all my hot streams and all my cool streams. So it will be 10 plus 20 plus 40 minus 30 minus 8. And this value is 32. And then my delta H will be 32 multiplied by 10, 320. 6, it's from 65, so initial temperature is 65. Delta H of this interval is 5, right? 65, 60 is 5. And in this case, my two hot streams are H2 and H3, so it's 20 plus 40 minus C1 and C2 minus 30 minus 8. So this is equal to 22 right here. And my delta H will be 22 multiplied by delta T. And this is equal to 110. Interval 7, 60, initial temperature is 60. Delta T is 60 from 35 is, or 62, 35 is what, 25. And summation of Cp hot, I have two hot streams, H2 and H3. So 20 plus 40 minus one cold stream, which is C2, which is 8. So 20 plus 40 minus 8. This is equal to 52. And then delta H will be 52 multiplied by 25. And this is 1300. And then finally, my last interval, interval 8 here. The initial temperature is 35. My delta T will be 35 minus 20 is 15. Summation of CP hot minus CP cold. I only have one hot stream, which is H3. And H3 has a CP of 40. So my delta H in this case will be 40 multiplied by 15, which is 600. Okay, so now I have my interval table. I have all my intervals. I have all the interval enthalpies. So I have all the information I need to build my cascade diagram. Okay. So I saved this page. I'm gonna erase this table. I don't need it anymore. And I'm gonna draw my cascade diagram on this side. Okay. So when drawing your cascade diagram, the first step is draw a number of boxes equivalent to a number of intervals. Really, this is the easiest way to avoid making mistakes when filling it out. So I have 8 intervals. I'm gonna draw 8 boxes. So I have 1, 2, 3, 4, 5, 6, 7, 8. And then I'm gonna draw lines or arrows connecting all of these boxes. And this is the basic structure of this cascade diagram. Okay, so now let's populate it. So on the left-hand side, I'm gonna write my initial temperature of each interval, and then in every box, I'm gonna write the enthalpy in each interval. So in this guy, first interval, my initial temperature is 185. Delta H is 450. Then I move on to the second interval. My initial temperature is 140. Delta H is 1200. Then my third interval, initial temperature is 100. The delta H is 0. Okay. Then okay, we can number them 1, 2, 3, 4 if you want. Doesn't matter. Then this guy, the initial temperature is 90. And then the delta H is 120. This guy, initial temperature is 75. So I'm here. I'm at interval 5. Delta H is 320. Afterwards, I have 65. And the delta H is 110. After that, I have 60, right? And the delta H is 1300. Wait, how is this possible? 15 minus 8, this guy is minus 120. So this, yeah, just be careful. So 15 minus 8, this is minus 1. 760, so initial temperature 60 and delta H in this interval is 1300. And then finally I have my temperature is 35 and the delta H for the last interval is 600. Okay, so I populated this table. So now let's calculate the Qs at each interval, or basically the heat available in each interval. So initially I'm gonna start with QH equals 0. Q1 will be 0 plus 450, 450. Q2 will be 450 plus 1200. This is 1650, and all of these are in kilowatts. Q3, 1650 plus 0, 1650, Q4 1650 minus 120. This is 1530. Q5 1530 plus 320, 1850. Q6 1850 plus 110. This is 1960. Q7 1960 plus 1300. This is 3260. And then Q8 or QC basically. QC is 3260 plus 600, right? This is 3860. Okay. So hopefully we didn't do any calculation. This is only -1, which we caught here, so that's fine. So this is the only, sorry, so after populating the cascade diagram, calculating all the Qs at every interval, let's have a look at what's going on here. So what I'm looking for is I'm looking for the most negative Q or a 0 Q. So in this case, all of them are actually positive, right? And I only have a 0 Q at the very top. So in this type of scenario, and it's a common scenario, this is called you know, this is called only a below pinch type of problem, right? So the entire system only exists below the pinch. And this is a common type of problem. You'll see this a lot in process industries where my pinch point is actually my highest possible temperature, especially if you have a highly exothermic reactor or something. Anyways, so in this case, my pinch point is just the very top of the street, right? So my cold pinch will be 185, and my hot pinch will be 185 plus 15, which is the delta T minimum. So this will be 200. And my energy requirements in this case, I'm going to have QH equals 0, and QC is equal to 3860 kilowatts. And in this type of problem, the entire problem is below the pitch. And this is common, right? So don't be surprised if you see this. What's uncommon is having the entire problem above the pinch. This is, you're not going to see this because it's not a realistic scenario, but this type of scenario is common, so just don't be surprised. Okay, so I'm going to save this. So now we have our three metrics here. I have my pinch point, I have my QH, I have my QC. So now let's just let's build our cascade, our heat exchange network, right? So I have my cold pinch temperature is 185. My hot pinch is 200. QH for this problem is 0. QC for this problem is 3860 kilowatts. Good. So now we're going to build our heat exchange network. Save this guy, clear everything, and let's start the second part of this problem. Okay, so to build your network, again, graphically, same approach. I'm going to just draw my streams. So in this case, I have my H1 stream. It goes from 200 to 80, and give yourself some space with these drawings, right? Especially if you're doing it with pencil, erase, you need to give yourself some space. H2 goes from 155 to 50. H3 goes from 90 all the way to 35. H4, sorry, now we have C1, right? C1 goes from 60 to 100. 60 to 100, and finally I have C2 going from 35 to 90. Right? 35 to 90. And let's write on the side here our energy or the metrics we got from our cascade diagram. So we said my cold pinch, right? TC, my cold pinch in this case is 185 degrees Celsius. My hot pinch, 200 degrees Celsius. QH is equal to 0. QC, 3860 kilowatts. And you know, since the entire problem is below the pinch, you don't really need to draw your two lines. You just need to acknowledge that the entire system is below the pinch. However, you just always remember the rules of the game below the pinch, right? So we said below the pinch, CP hot has to always be greater than CP cold, greater than or equal to CP cold. And the second rule, we said that there is no heating below the pinch, right? Should never heat below the pinch. Plus, no. And just remember this no heating and no cooling rule, because it's also a common error. You're tempted to heat below the pinch or cool above the pinch to make your numbers match. If the numbers having a hard time matching the numbers, split your streams and take it from there. But you should never heat below the pinch. Thermodynamically impossible, right? Thermodynamically it won't work, right? You either need a heat exchanger which is over-designed, or you need to use a lot more utilities than you need. It just doesn't make sense. Okay. Anyways, so before matching, let's write our parameters. So I'm gonna write my CP, and then it's up to you if you want to draw them on the diagram or not. But I always do it. I think it makes it easier, just having everything in front of you. So the CP here, CP for these streams are 10, 20, 40. So I have 10, 20, 40, and then I have 30 and 8. Okay. And let's also calculate the amount of heat available in each stream, right? So I have 200 minus 80 multiplied by 10 for the first guy. So it's 1200 kilowatts. For the second stream, I have, this is 155 minus 50 multiplied by 20, that's 2100 kilowatts. 90 minus 35 multiplied by 40, 2200. I have 60 to 100 for 100 minus 60 multiplied by 30. This is 1200. And then 90 minus 35 multiplied by 8. This is 440. Okay. So now I have everything. Let's start matching these streams. Let's start doing the matching. And the rule of this matching is CP hot has to be greater than CP cold. Let's have a look at H1. CP for H1 is 10. Okay, let's have a look at the first cold stream, C1, 10 versus 30. Is this rule satisfied? No, so I cannot match H1 with C1. Let's move on to C2. 10 versus 8. CP hot greater than CP cold. This rule applies. So I can match H1 with C2 actually. Okay, so let's match these guys. Sorry. Yeah, so I can match H1 and C2 because, you know, 10 is greater than 8, so I'm going to connect it. Sorry, a heat exchanger here from H1 all the way to C2. So H1 has 1200 kilowatts to give. H2 needs 440 only. So I'm only going to transfer 440 kilowatts. And this way C2 is done. It met all its energy needs, so I don't need to connect anything else to it. And I still have some energy left in H1, right? So how much energy do I have left? 1200 minus 440. Sorry, I have 760 left in H1. Okay, H2. So can I connect H2 to C2, C1, sorry. So to H2 has a heat capacity of 20. C1 has a heat capacity of 30. So 20 to 30, can I make this match? I can't. So H2 doesn't work. H2 to C1 doesn't work. How about H2 to C2? There is no energy available in C2. It's done already from H1. So I can't really make any connections with H2. So let's leave it for now. Let's move on to H3. So H3 versus C1. So H3 has a heat capacity of 40. C1 has a heat capacity of 30. So is 40 greater than 30 to make this rule? It is. So let's connect these two guys. So I'm going to connect the heat exchanger from H3 all the way to C1. And how much energy is being transferred here? So H3 has 2200, C1 needs 1200. So I'm going to just transfer 1200 from H3 to C1. This way C1 has all its energy requirements met. And H3, I still have 1000 left to be met. Okay, so now I did my matching. Both my cool streams are done. And I have some energy left in these guys. So since it's below the pinch, I can cool. So I'm going to add 3 coolers here. So I'm going to add 3 coolers, 1 on each stream to just satisfy or just to remove this excess energy. So QC here will be 760. This way, 760 plus 440 is 1200. This way H1 is done. I'm going to add a cooler on this stream. H2, I wasn't able to connect it to anything. So I'm just going to add a cooler to remove all of this heat. So this will be 2100. And then with H3, I'm going to add a cooler to remove the remaining 1000 kilowatts left. 1000 kilowatts. So I added 3 coolers, and let's check our calculations. So to check if our calculations are valid, then these 3 numbers should add up to my minimum cooling utility here, right? So let's check it. QC will be 760 plus 2100 plus 1000, and this number will be equal to 3860, which matches the number I got from my cascade diagram. So this means my system is valid and this system will achieve these targets. Okay. So this is problem number 2. The unique thing about this problem was that the entire problem was below the pinch, and this might be a problem you get. Usually these problems are easier. The only curveball you can get in this type of problem where it's entirely below the pinch is if you need to do a split stream for one of the cool streams to meet your matching targets. But generally, it's just one problem and you just match your streams and you're done. Okay. So yes.
I have a question. So for your heat exchanger network, is this the primarily what you want us to present, where it has the coolers and the heaters on the streams, or do you want us to include the cascade as well?
So when solving the problem, you will have to develop the cascade to get here, right?
Yeah, I wasn't sure if you wanted us to include it as like the final answer, because I know you have to go through it, but
I mean, you just show your work all the way to the end and you submit everything you worked, you wrote, right?
okay.
Yeah, so on an exam, I mean, I expect you to just work through the steps on a piece of paper and then just submit your work where you show all the steps or maybe have some comments next to it or whatever, okay?
Okay, got you.
Does anyone else have a question? Okay, that's fine. So we're done with this problem. And again, same approach, just follow the steps. The main tripping points here is doing a simple arithmetic error. Like when we were building the graph, I forgot the minus. I forget the small minus. When I do the matching here, this number is different than this number. I have to go back and repeat the entire thing and check through all these numbers, all these calculations. So, just do it slowly. Don't rush through it, right? You want to minimize simple mistakes. Okay. Let me save this and let's move on to the third problem. in the problem set. So let me share my screen here. Problem set. Okay. All right, so this is the third problem. This is actually the problem I gave him on last year's exam. So I have 3 hot streams and 3 cold streams. And I'm given a delta T minimum of 15 Celsius. And this is the type of problem you're gonna get. To build the interval table, you get 20 points, you build a cascade diagram, determine your pinch points, minimum heating, minimum cooling requirement, there's also a bunch of points, and then finally develop your heat exchange network, okay? So let's go through the steps for this system, and let's design this problem. So let me move to the whiteboard here. Okay, so this is problem number 3 in this set. So I have problem 3, and I'm given a bunch of streams again. Stream name, I have my T source, degree Celsius, my T target, degree Celsius, and my CP, or my C in kilowatt per degree Celsius. And in this case, I have H1, H2, H3, C1, C2, C3, and my source temperatures were 190, 205, 105, 65, 15, 40. My T target were 30, 80, 55, 175, 90, and 130. And these guys are 25, 8, 44, 32, 17, 21. Okay, and I'm given the delta T minimum to be equal to 15 degrees Celsius. So let's go through the steps. Let's solve this problem. So first step is always remove delta T minimum from my hot streams. And only the hot streams, don't subtract them from the cold streams. You might, you know, if having a long day, you might just going through the motions and just subtract the delta T minimum from everything. Doesn't work. So this will be now 90 minus 15, this is 175. 30 minus 15, this is 15. 205 minus 15, 190. 80 minus 15, 65. 105 minus 15, this is 90, right? And 55 minus 15, this is 40, right? So I've subtracted 15 from all my streams. And yeah, so I just removed delta T from all my streams here. Okay, now step 2 will be to arrange your temperatures from highest to lowest, and we're gonna plot the streams on after arranging them to just identify my intervals and just start building my interval table. Okay, so let's arrange them from highest to lowest. My highest temperature here is 190. So I have 190 done. Second highest is 175. 190, 175. Third highest is 130. Right, so I have 190, 175, 130, and also this 175 is done. Then I have 90, right? I have 90, so this guy and this guy, they're okay. Then I have 65, 65. Then I have 40, right? And then finally 50. 15 between these two. So we didn't miss any temperatures. Okay, so I just arrange them from highest to lowest, and then I'm gonna graphically just draw a straight line next to each interval here, or next to each temperature. And once we do this, you can see that we have, how many intervals do we have? I have, this is my first interval, second, third, fourth, fifth, sixth. So I have 6 intervals in this problem. Okay. Hopefully, so 190, 75, 30, 15. I'm just going through the calculations again. Okay, good. So now let's plot the streams. Let's plot the streams. I have H1. Sorry about that. I have H1, H2, H3, C1, C2, C3. H1 is from 175 to 15. So I'm just plotting 175 all the way to 15. H2 is from 190 to 65. So I have 190 all the way to 65. H3 is from 90 to 40. From 90 to 40. C1 is from 65 to 175. So I have 175 all the way to 65. C2 is from 15 to 90, right? C2 goes from 15 or from 90 to 15, doesn't matter, 90 all the way to 15. And C3 is from 40 to 130. Nope, it's the wrong connection. So I need 40 to 130. 130, right? So C3 is from 40 to 130, C2 is from 90 to 15. C1 is from 65 to 175, H3 is from 90 to 40, H2 is from 190 to 65, and H1 is from 175 to 15. Okay, so I have all my streams drawn on this interval sketch. So now let's build our interval table, right? So our interval table here we go. So I have my interval number. Interval number, I have my initial temperature, I have my delta T, I have summation of Cp hot minus summation of Cp cooled, and I have my enthalpy across each interval. Okay. So for interval 1, my initial temperature is 190. My delta T in this case, 190 minus 175 was 15, right? Summation of Cp hot minus summation of Cp cooled. So I have one hot stream, H2 right here, and the Cp for the stream is 8. So in this case, it's 8, and delta H will be 15 multiplied by 8, it's 120. Okay, interval 2, the initial temperature is 175. The delta T of this interval 175 minus 130 is 45. Summation of Cp hot minus summation of Cp cooled, I have H1 and H2, so 25 plus 8 minus C1, which is 32. So this value is 1, so delta H in this case is 45. Interval 3, my initial temperature is 130. My delta H 130 minus 90 is 40. Summation of Cp hot minus Cp cooled in the stream will be H1 plus H2 minus C1 minus C3. So H1 is 28 plus H2, which is 8, minus C1, which is 32, minus C3, which is 21. So this value is minus 20. And delta H will be minus 20 multiplied by 40 minus 800. Interval 4, initial temperature is 90. Delta T for this interval 90 minus 65, this is 25. And here I have all of the guys are here, right? So I have H1 plus H2 plus H3 minus C1 minus C2 minus C3. So let's do it. 25 plus 8 plus 44 minus 32 minus 17 minus 21. And this is equal to 7. And delta H will be 7 multiplied by 25. This is 175. Interval 5, initial temperature is 65. The delta T for this case is 25 as well, or for this interval. And summation of Cp hot minus Cp cooled, I have H1 plus H3 minus C2 minus C3. I have H1, which is 25, plus H3, which is 44, minus C2, which is 17, minus C3, which is 21. And this gives a value of 31. And delta H in this case will be 31 multiplied by 25, which is 775. And then finally I have 6, or the last interval, interval 6, initial temperature is 40. The delta T for the stream is 40 minus 15, which is 25 again. Summation of Cp hot minus Cp cooled, I have H1 and I have C2. So H1 minus C2, H1 is 25, C2 is 17. So this is 8, and 8 multiplied by 25, this will give me 200. Okay, so this is the overall interval table for this system. So once we get to the interval table, now is the time to plot or draw the cascade diagram. Okay, so I'm gonna erase this figure right here and I'm gonna start drawing the cascade diagram. Okay. So again, first step in drawing the cascade diagram is to draw a number of boxes equal to a number of intervals, right? This minimizes any sort of errors if you're doing it step by step. So I have 1, 2, 3, 4, 5, 6, and then I'm gonna connect them with a bunch of arrows here. Right, 1, 2, 3, 4, 5, 6. And now let's populate the information we have on the table or move it to the cascade diagram. So on the left-hand side, I'm gonna write my temperatures, 190, and inside the box, I'm gonna write my delta H. Delta H is equal to 120. Then I have 175 and 45. And then I have 130 and minus 800, right? Let's write these guys properly. So here I have delta H is equal to 45. Here I have delta H is equal to minus 800. Then afterwards I have my initial temperature of this interval is 90, and the delta H is equal to 175. Here I have the initial temperature of this interval is 65, and delta H is equal to 775. For the last interval, the initial temperature is 40, right? And delta H is equal to 200. Okay, so I have all of these numbers here. After getting all these numbers, let's calculate the heats. So initially I have my QH is equal to 0. My Q1 in this interval will be 0 plus 120, so it's 120. My Q2 will be 120 plus 45. This is 165. My Q3 will be 165 minus 800. This is minus 635. My Q4 will be minus 635 plus 175. This will be minus 460. Q5 in this case, minus 460 plus 775 is 315. And finally, my QC will be 315 plus 200, which is 550. Okay, hopefully we didn't do any arithmetic errors here. Let's just see, 875, 31. So I think we have everything. Just have a look here. Should have the solution somewhere. Anyways, doesn't matter. If we make any errors, we'll go and retrace. So once we have your cascade diagram populated, what you're looking for is the most negative point. So in this case, the most negative point is, 0, 120, 160 minus 635 is the most negative point, and this will be my pinch point. So this here will be my pinch point, and my cooled pinch will be 90, and my hot pinch will be 90 plus delta T minimum, which is 15. So it's going to be 105. So these are my pinch points. And of course, they're in Celsius. Keep a note of the units. And then to determine my minimum utilities, I need to add enough heat so that this value becomes 0. So I need to add 635, right? Plus 635. Sorry. So this will be equal to 635 kilowatts plus 635. And then once you add it at the top, it's going to cascade all the way down. 635 plus 120, it's going to be 775 plus 635 here. So I have 165 plus 635. This is 800 plus 635. This is 0 plus 635 here. 175 plus 635 here is 950. And then finally plus 635 at the bottom here. This will be 1150. So now I have my pinch point and I have my minimum heating and minimum cooling requirements, and this should be enough to start building the heat exchange network. So let me save this page. Let me clear all of these. Let me write them down here on the side, and then we can start building the network. So we said the pinch point was 90, QH 635, and QC was 1150. Okay, good. So now let's plot this system, or let's draw our heat exchange network. Okay, so I'm going to clear everything, and now let's start drawing this heat exchange network for the system. Okay, so again, we're going to follow the same steps to draw the heat exchange network. First of all, so let's just write them down. QH 635, QC we said was 1150. T pinch was 90 and 105 for cold and hot. Okay, so let's draw it. So I have H1 here. It goes from 190 all the way to 30. H2 goes from 205 all the way to 80. H3 goes from 105 to 55. And again, I'm using the original temperatures. I'm not using the adjusted temperatures, which we did to develop our cascade diagram. C1 goes from 65 to 175, right? C2, it goes from 15 to 90. And you have C3, which goes from 40 all the way to 130. Okay, so once we plot our streams, I'm gonna draw two lines for the pinch point, or basically one line to divide it into above the pinch and one line to divide it into below the pinch, right? That's the logic of drawing two lines. If you want to draw one line, it's fine. But basically the logic of having two lines is just splitting this problem into two parts. Okay, so we draw our lines. So for the hot streams, we said the pinch point was 105. So I'm gonna write the temperatures on both sides, 105 for the hot streams. And then for the cold streams, we said the pinch point is 90. So I'm gonna write 90. And once we get to this point, I'm gonna go over this diagram and clean it up. So for the first stream, I have 190 to 105, 105 to 30, that's fine. 205 to 105, 105 to 80, that's fine as well. 105 to 50, 105 to 105, so H3 does not exist above the pinch, H3 only exists below the pinch. So I'm gonna redraw H3 here. It goes only from, sorry about that, only goes from 105 all the way to 55.
So Dr. Basha, is that because it can't go from 105 to 105?
Yeah, but it's the same temperature, right? So H3 starts at the pinch and only exists below the pinch.
Okay.
Because basically, if you draw it from 105 to 105 and you want to calculate the enthalpy, which is Cp delta T is 0. So there is no heat really available above the pinch. So there's no point drawing it. Okay. So I have, for C1, it's from 65 to 90, 90 to 175. That's fine. C2, 15 to 90, 90 to 90. Again, same idea. So C2 only exists below the pinch. So I'm going to erase C2 from above because there is no heat available to be transferred here, right? So there's no point really drawing it above the pinch. So I'm just going to draw C2 from 15 all the way to my pinch point. And finally C3, 40 to 90, 90 to 130. So this is fine. So now I have my system, which is ready to start doing our matching procedure. Okay, so let's match, or before matching, usually I like writing the CP values and calculating the amount of enthalpy available above and below the pinch for each stream. So no one's getting it anymore. So the CP values for the 6 streams are 25, 8, 44, 32, 17, 21. And the delta H, I'm gonna write the delta H values both above and below the pinch. So above the pinch here, 190 minus 190 minus 105 multiplied by 25. This is 2125. And the second for H2, it's 205 minus 105 multiplied by 8. So I have 800 here. For H3, there's nothing. For C1, it's 175 minus 90 multiplied by 32. So I have 2720. For C2, doesn't exist above the pinch. And then finally for C3, 130 minus 90 multiplied by 21. So amount of heat available here is 840. I'm going to do the same thing below the pinch. So 30 or 105 minus 30, 75 multiplied by CP for each one. So it's 1875. For H2, 80 to 105. So 105 minus 80, 25 multiplied by the CP, which is 8. So I get 200. For H3, 105 minus 55 multiplied by 44, which is 2200. for C1, 90 minus 65 multiplied by 32. So this is 800. C2, 90 minus 15 multiplied by 17. This is 1275. And then finally C3, 90 minus 40 multiplied by 21. This is 1000. Okay. Just double check these numbers. Okay, and then okay, so the numbers look fine. So now let's start the matching procedure or building our heat exchange network. So before doing so let's write the rules here. So I'm going to say above the pinch, CP hot has to be less than CP cooled, and there is absolutely no cooling above the pinch, right? And below the pinch, sorry, CP hot has to be greater than or equal to CP cooled, and there's absolutely no heating below the pinch. Okay, so now let's start the matching procedure. Let's have a look here. So I'm going to start with H1. H1 had a CP of 25. I'm going to compare it to the first cold stream available above the pinch, which is C1. 25 versus 32. Is this match possible? So 25 is less than 32. So this match is possible. So I'm going to connect these two streams. So I'm going to connect the heat exchanger from this guy, from H1, sorry, to C1. And how much heat should I transfer? So H1 has 2125, C1 needs 2720. So I'm going to move all the energy from H1. This way H1 is done above the pinch. And C1, I gave it some energy and I still have some energy left. So how much energy do I have left? 2720 minus 2125. So I have 595 kilowatts left for C1. Okay, let's have a look at H2. So H2 has a CP of 8. And so yeah, so H1 is done. H2 has a CP of 8. Let's see, can I transfer from H2 all the way to C1? So is the CP of H2 lower than the CP of C1? 8 is less than 32, so I can do this transfer. So we can transfer all of the heat from H2 to C1. However, you have another option. So let's have a look at C3 as well. So can I transfer heat from H2 to C3? So the CP for H2 is 8. CP for C3 is 21. So I can do this match as well. So let's have a look which is the better match in this case. So, I mean, both of them are valid. If you write either on the test, it's okay. But let's just have a little discussion here. So this guy has 800 kilowatts. This guy needs 585. So if I connect H2 to C1, I'm going to transfer 595 to satisfy C1. And then I'm going to need to connect a third heat exchanger from H2 to C3 to get rid of all this heat because there is no cooling above the pinch. Alternatively, if I connect H2 directly to C3, I can move all of the 800 from here to here. And this way I only have one heat exchanger for H2. So logically, it makes sense to only connect a single heat exchanger from H2 to C3. And you can try both combinations. Both combinations are valid. In terms of heat exchange area, you're going to get the same heat exchange area. So cost-wise, they'll be very comparable, but ideally you want to minimize your number of heat exchangers. So if I connect H2 to C3, H2 has 800, C3 needs 840. So I'm going to transfer, 800 from H2 to C3. This way H2 is done. and C3 still has 40 kilowatts left. So in order to satisfy this remaining requirement, I'm going to add 2 heaters below the pinch. The first heater will provide 595, and the second heater here will provide 40 kilowatts. And if I sum all these heaters, 40 plus 595 is equal to 635 kilowatts, which is the same number as I got from my cascade diagram. So this match above the pinch is valid. Okay, let's have a look below the pinch here. So in this case, CP hot has to be greater than CP cooled. So let's compare the first hot stream to my first cool stream. H1 has a CP of, let's write the CPs here, 25, 8, 44, 32, 17. Okay, so let's have a look, 25 to 32. CP hot greater than CP cooled? No, so I can't really connect these two guys. Let's have a look, H1 to C2, 25 and 17. Can I connect them? Yeah, so 25 is greater than 17. So I can connect these two streams. So let's connect, put our first heat exchanger below the pinch here between H1 and C2. H1 has 1875, C2 requires 1275. So I'm gonna move 1275 basically from the hot stream to the cold stream. This way C2 is done. I'm at its energy requirements. Now let's have a look at C3. I can connect another heat exchanger to move the rest of the energy from H1 to C3, or I can look at H3 here. H3 has a heat capacity of 44. This is very high, right? It's the highest one in the bunch. So it can technically transfer heat to any of these cool streams. So let's try to get rid of the heat in H3. So I'm going to do this. H3 to C1, I can make this connection. So I'm going to connect the heat exchanger from H3 to C1. I'm going to move 800 kilowatts here. And then I'm also going to connect H3 to C3. And I'm going to move 1050, right? I'm going to move, where's the mouse? So I'm going to move 1050 from H3 to C3. This way, both C1 and C3 are done. So I transferred all the heat. And in H3, do I have some heat left? So I have 150 plus 800. So I transferred 1850. 2200 minus 1850. I still have some 50 kilowatts left in this stream. And in this stream, in H1, how many kilowatts do I have? 1875 minus 1275 is 600. So I still have some energy in the hot stream. So in this case, I can cool below the pinch because all my cool streams are satisfied. So that's good. So let's cool these hot streams below the pinch. So I'm going to add the first cooler, 600 to meet the rest of this energy. I'm going to add the second cooler here with 200 to meet this energy requirement for H2. And I'm going to add a third cooler here with 350 to meet this energy requirement for H3. And let's double check our answers. So summation of QC, 600 plus 200 plus 350. This will be equal to 1150 kilowatts, which is the same number we got from our cascade diagram. So this connection or this system is valid below the pinch. So this network is the optimum network. Of course, as we've seen, or as we're discussing this, we have a bunch of alternatives. So you can have a variation of this network. So if you want, you can connect H1 to maybe C3 and then have a bigger cooler on this stream, or you can connect H1 to C3 here as well and have a bigger heater on this stream. It doesn't matter, you have a bunch of variations. However, your overall number of units will be the same, so try it out. you're going to find out that the overall number of units, heat exchangers plus heaters plus coolers will all be the same, and this system will achieve your minimum energy requirements. Okay, so this is the end of these types of, or of this problem set. Before closing or before ending this session, someone has asked me about problem number 4 from the previous homework and how we had 2 pinch points in that case. So I just want to make a comment that if you have 2 pinch points, always take the higher pinch point, okay? And design your system, make sure your energetics match, and you should be fine. You're not gonna get a problem like this on the test, so don't worry about it. But usually when you have a higher pinch point, it means that the delta T minimum value you choose is actually what's the best way to put it? Or basically means you can operate your system at a larger delta T minimum value, right? You have a pinch point spanning 2 intervals. It means that you can operate the system probably with a higher driving force, and you could probably use better coolants and things like that. You're not going to get this on the test, so don't overthink it. Just worry about these types of problems. The split is something you might see. Having an entire system below the pinch is something you might see, and just having a normal system where you just connect all your streams is also something you're going to get, or something. So this type, problem number 3, you're 100% going to get something similar. 1 and 2, you might get a problem with, well, having some of these variations. Okay, so I think we're at 1 p.m., right? Is this the end of the lecture? I think this is the end time, right? Or is it 1:30? Yeah, we still have time to 1:30. So if you have any questions, you can ask them. I'm going to answer them. Otherwise, I'm gonna stop here, and I'm gonna put out a survey this evening, just taking your opinions if you want to have a test next week, or we can push it to the week after and have an extra review session as well next week. Okay. So if you don't have any questions, thank you very much, and session has ended.
Dr. Basha, I had a quick question in regards to problem number 2.
Okay.
It was just one step that I missed. For the interval number 6.
Okay, let me open the solutions we had. It's problem number 2.
In regards to the interval table?
Okay, yeah, I'm just opening it up.
Okay.